just real quick before we begin, the Behrens-Fisher homework, I listed the MATLAB code. From last time, here it all is. You'll get a text file or something like that if you don't have MATLAB launched. I'll just remind you that there's case 1, case 2, case 2b, all these different cases. It says what the cases are. I didn't put those in conditional statements as promised. But you can take this code. This should be a pretty easy exercise to code up. And so this is just a reminder. This is all built for the one-sided case. It does tell you what the null hypothesis is up here. So this is really equals is what most classicists will write because they'll take the supremum over that set. But what they're really testing are these two things. And so technically, I see the test as being this. What you'll usually see is equal right here. And if you've taken a formal inference class, you'll know why they do that. For Bayesian, it's really quite literal writing it down this way. But keep in mind the classicists can only plug in one number. So which number do they plug in? The most informative number, the boundary. So that's the technical nuance there. I didn't quite understand that for a long time. And my homework suggestion is the extra credit. How does the Bayesian Gibbs implemented one-sided test compare? So you can do that. I'm going to write this down in about a half page for you, so I'll get to a PDF version. And you have to define what it means to compare, but this problem's already set up for you. Look at the type 1 errors. So compare the type 1 errors. And if anything else you want to compare, that's good. If you can't think how to compare things or what should be compared, you're going to have a hard time being a statistician. That is like the one big skill that we should compare this and not that. And there's reasons why. So, and then I'm going to ask you for 5% additional extra credit. It's much harder than the first one. Do this in the point null setting. So now there's a couple little things that you have to choose when you're doing all of this. So what is the prior on the null and the alternative, and then how did you smear mass, i.e. how did you formulate the alternative prior? If it were me and I was just trying to collect 5% extra credit, I would just take the conjugate form. If I were trying to understand all the nuances and treat it as a real research problem, I'd grab Val's form. I'll put that paper up for you. I'd grab a whole bunch of them. But if you just want to get through this in a few hours and collect some credit, there's fast ways and slow ways through it. So real research is excruciatingly slow because you're checking every little corner of the problem. Okay, so that's something you can play around with over break. It will be due at the final also, so you've got plenty of time, but I would start early. The next homework, the one that's current right now, that does take a while. And so that mixture model, you might be chasing bugs for 20 hours. You might be done in 15 minutes. It's just one of those things. How much experience do you have? You've done it before. It's kind of one of those. Sorry, not sorry sort of thing. I mean, because the only way you get good at it is you struggle. So if you haven't spent your 20 hours yet on chasing one little bug, you know, it awaits you. So if you have, you won't forget these things and you'll become better stylistically, better practice, better organization as you go through everything. Okay, just a couple questions about p-values and posteriors before moving on. I've given you a couple bazookas on how you can game science. I do not consider it science. However, I do see a lot of people doing this stuff. So for a p-value, just ask these questions real quick. For a p-value, how can you make it smaller?
Cranking n up.
Yeah. So crank n up. Now there's a couple things I need to say about this for answers. Now again, this is not science, this is how you game science. So if you see somebody compute a p-value, you want to know what is their distribution, why did they use it, is it approximate, is it exact? And if you want to check the performance, you probably need to set up a simulation study to understand these things in general. Theoretician might come to you and show you a bunch of asymptotics and tell you that in theory all this should work. You should still check. So because a lot of things in theory work and they don't work for your specific case. supposed to, but you don't have quite the properties. So if the alternative is true, this is enough to establish, and this should happen, that as I get bigger and bigger n, I can tell that the null is not true, and I favor it in exchange for the alternative. If the null is true, then the p-value is uniformly distributed, so it's bouncing around. So cranking it up is not enough just to do it, but you have to do it sequentially. Make it big, see what your p-value is. If it's not small enough, make it bigger. Double it, something like that. Come up with some systematic rule. Check p. Eventually, it'll duck alpha, because it's uniformly distributed. So you're just playing this random lottery. Is it small enough? Is it small enough? Is it small enough? So if the null is true, and the model that you're using is correct, which that's a big assumption sometimes, or close enough to be correct, then uniformly distributed and sequentially marching through it until you get a big enough p-value. Fortunately, we see people do this all the time in science. So what I'm really checking is if you know to question somebody on this. How'd you pick your null model? Is it right? How did you pick n? If they say something like, well, we didn't see we didn't get a significant result, so then we did the power calculation and we noticed that our power only had 80%, power. So to detect that small difference, so that power calculation is 1 minus the type 2 error. So some people say it's the power to detect that the null is true in the first place. That's where that language comes from. They'll say, well, I have a 20% type 2 error rate effectively. My power's only 80%, so I better go get more n. And so they'll phrase it in a way that sounds scientific. But if they didn't start out with that, and they've changed the game, the rules of their stopping rule in the middle of their stochastic process, I don't believe anything. I don't care what your last rule was, the rule that you finally settled on. I care about the whole sequence of rules. Okay, so question and this is for the point null problem. Both of these questions pertain to this. How does the Bayesian and I'll ask this in the opposite manner, get a large posterior probability? So I might write this down as probability of H naught given my data. So again, the null is sharp. This is the very contentious test that nobody can even determine what they're even talking about when they ask this question. One-sided thing is well phrased, I will say. So this one, what's close, is what we're all disagreeing about. I think we really do mean close in most situations. We did have an interesting conversation about physicists, and they're really trying to detect absolute error. So this Higgs boson thing where they said, we're looking for p-values as small as 0.00001 or something ridiculously small. So they weren't looking for absolute deviations, and they had huge sample sizes, and that's what they wanted to know. Most scientists are asking what's close. Is it close enough? Compared to what? Maybe the existing scientific literature, whatever is posted there. Or do I think of something different? So I tend to think everything needs to be comparative. But how does a Bayesian get a large posterior? I can game the system. Cherry pick your data. That's too egregious, right? That's just, you're fired. So everybody knows that one. And so we do see people in their careers on this. So we've seen some huge instances of this. I've had friends that have been racked up in it. So over at Duke, there was a huge scandal quite a few years ago where in the bioinformatics complex, somebody had been using some fictitious data, sending it off to my buddies in the statistics department and having them analyze it, but they had already massaged it. So then they got the okay, published in these 20-person consortiums, and got caught eventually. So that one will get you federally prosecuted if you get caught doing it, because you're taking governmental money. So they don't like that. You can do a whistleblower suit on them. That's what ends up happening. So, careful. So people have gone to prison over falsifying data. This one won't put you in jail. So, some of my Bayesian friends think it should, probably. We'll go a little lighter, but at least as we understand this stuff. So if somebody asked me to testify in 20 years on your career, did they understand this issue? Let's say yes. It's not going to happen. But how does a Bayesian get a large posterior? Say they want to support the null, what would you do? I've given you this answer a million times already. You're going to break my heart if nobody knows it. I know Annie knows it, right? You do.
Increase psi.
Yeah, exactly. Alternative variance, blow it up, make it big. Diffuse the alternative prior. So here's the answer. That's how you do this. So bad science. So if you see somebody doing this Bayesian thing, you want to understand how they calibrate their alternative. That's the question you're going to ask them. If they go, well, I just picked one. I guess this seemed like a good choice. You just picked one. You just picked an arbitrary number, too, for your posterior. So if they say, I standardized everything and blah, 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 so I was looking, so my result means relative to one standard error or something like that, that's what I'm talking about. If they tell you all that and they've done everything and they explain it in the right way, they get passed. If they say just picked it for arbitrary reasons, whatever that posterior probability is arbitrary as well. So there's a big conflict here, and that conflict is usually described as the Bartlett-Lindley paradox. Lindley and Bartlett said slightly different things. Bartlett paradox is very specific to increasing psi, and Lindley said more general things about all this. Okay. So lots of issues there. Let me tell you one more issue before we do something new and fun. So just Bayes factors in general. So Bayes factor So when I hear people say Bayes factor, I hear posterior probability. I don't know what, if somebody says they have a Bayes factor of, 72, I don't know how I feel about that. I could look at Rafferty's guidelines, say, moderate information against the null or something like that, or in support of the null. I like to compute it on a probability scale. We all seem to talk that language. It's a convention that we're used to, so I like it. So a Bayes factor is just this. So Bayes factor is going to be the integral of your likelihood function, theta, given your data. Your prior probability, so how I smear mass on the null space, d theta, divided by integral likelihood data, H alternative, the prior, how I smear mass across that space. Just to be really specific, I'm only integrating over the null space and I'm only integrating over the alternative space here. So this is what a Bayes factor is. In the point mass case, there was only one way to smear mass on the null space. But I can compare two different spaces arbitrarily. Sometimes we compare a space with a lot of values against a space with just one value. Very common. Sometimes we compare spaces with equal numbers of values, or however you want to do it. But in general, this is the Bayes factor. It's just this marginalization of the data. And so I like to write this down is sometimes like this. P H naught of my data, P H alternative of my data. They're data margins. But I want to point out that the priors you're using right here, let's imagine I was doing something like testing theta at its one-dimensional parameter, and I want to test it at just a point null. And I want to compare it against a big set. Well, notice that these two priors don't have the same normalizing constants. They will not cancel out. So that's a big problem. However, imagine something like this. we know if H naught is theta equal to theta naught, H alternative, theta something different, pi H alpha theta proportional to 1 is a bad prior. Just so that I can convince myself that I'm saying, why is that true?
Is that the reason we just talked?
Yes. For the same reason. Imagine this. Imagine you did just shove this thing in here. I said, that was 1. Whatever this number is that I compute is arbitrary. Let's imagine I just said, you know what? I don't like using 1. I like always multiplying by another flat thing. Let's make it 10. I put the 10 in right there. This Bayes factor would be 10 times smaller. So do not use diffuse priors and do not use arbitrary normalizing constants either. If it can't be normalized, you might need to check something really carefully. So this is a bad prior. So using 10 changes this value. And I've seen this in the literature, people reporting Bayes factors, and they have arbitrary constants that are showing up right here. Again, their analysis is bogus. You saw this all through the early 90s when people were just getting this tool for the first time. This is great. You know, I can move this thing around all kinds of ways. Bad science. Okay. But what about this case? But for H naught, theta is greater than theta naught versus H alternative, theta is less than theta naught, can we use pi H naught, I'll write down alternative for the first one, can I write this proportional to 1? Can I use my flat prior there? The answer is yes, but there's a condition. If
You make them the same.
I make them the same, I do the exact same thing to the null. Yes. If we let pi H naught theta also be proportional to 1. That would make sense to me. If I plug this one in as 10 and this one in as 1, you do not have the cancellation. So if the parameter appears in both the null and the alternative model, and they have the exact same meanings in both models, that parameter, it's the same parameter, then I can use an improper prior on it. If it appears in both the null and the alternative model. I would say when I have theta is equal to 0, that's what I mean by not appearing in the model. I'm substituting it with this number 0, and it doesn't have the same look and feel of what happens in the denominator. So here's what I'm saying mathematically. You can have arbitrary constants in your Bayes factors, so long as they cancel each other, then it's okay. If they do not cancel, I'm going to tell you why that is, because the parameter has a different interpretation in the two different models. And so that's really the bottom line. If you have priors that appear in both the null and the denominator, and there's some sort of balance between those two spaces, you're free to do that. And most people will use diffuse priors. But if they have very different cardinalities in these two different things and they normalize different, you won't have cancellation of your arbitrary factors that you built in. So the thing you want to do is the thing you cannot do. So build flat priors on this point mass null model sort of thing, because the priors in both the numerator and the denominator get treated very differently.
So is this also applicable for the point null mass? So if H0 is theta equal to theta 0 and H alternative is theta different than theta 0, can we also use improper priors if they are the same?
Somebody answer Christina's question.
No.
No. Nope, cannot.
They don't cancel out in that case?
They do not. That's the whole point. You have a whole bunch of arbitrariness. Try it out. You'll notice you'll have arbitrary terms that don't cancel each other. So again, just look at your math, inspect things, give it a common sense check, and defend your prior choices and see what they mean, how you're weighting things. I kind of like this choice right here. I could have used a conjugate prior right there, and I'd be testing things close to wherever I truncated the sides. I'd probably truncate them at theta naught. That's the only thing that matters. And I could just diffuse away from that thing. Saying that, I really like the properties of this prior for this, because I don't know what that variance is. I'll notice that everything cancels very, very nicely. So, anyway, that's all I have to say about Bayes factors. Arbitrary constants, if they appear in your Bayes factors, you've got a problem. Come and see me. Shoot me a note. I'll send you a paper. So, people making horrible errors. You might ask me, how do I come up with my prior? And I'm going to go, ha ha ha. That's your job. So, what is it about the science? What is it? So some people talk about elicitation, and they have these subjective rules for questioning people and giving them a battery of questions for being able to elicit their prior. Ryan, how do you feel about that field? You ever seen people do it?
No.
So it turns out our speaker a couple weeks ago is an elicitor. So he does elicitation. So Tony O'Hagan kind of preaches this. I've looked at it, I thought it was really cool. When I heard about it, I was like, ooh, like data psychology, prior psychology. I've never seen anybody carry this out effectively. And so you really need real reasons for calibrating your priors. If things cancel in numerators and denominators like they often do in estimation problems, then I don't really have a problem with it. So, but in model selection in general, you have to be a lot more careful. So, that's enough about that. Okay, let's move on to something else. So, approximate Bayesian computation. Okay, here's the setup. So, the problem. Let me tell you what the problem is that ABC hopes to overcome. Problem, you cannot write down up to proportionality likelihood theta given your data. I can't close form write that thing down. So, however, what you do have, so you might just say, if I can't write that down, I'm out of luck on everything. And that would be true. But you get something else. You get a proxy. I'll just write this down to be entirely clear. This is going to be proportional to fx given theta. So here's my sampling model. And this one's my likelihood. Okay, the first day of class breakthrough was if you can write that down, you've written this down. It's just kind of changing how you're thinking about the arguments. Change which argument it's a function of. That's all we're doing, but it has the same functional form. So usually my very cheap argument about the likelihood principle, this is not the likelihood principle. So I say, here's how I think about it. We have to skip that altogether, is that I like the relationships between, if I believe x's were generated from thetas using the functional form under f, I should use that same functional representation when I go to estimate thetas. I like that, that's good enough for me. So, nothing philosophical about that, just kind of makes sense. Let me add on something else. I also like to regularize my space. Because if I have just a little bit of data, my inferences go kind of haywire. I get one more data point, so I like to dampen everything. Dampening is a good physical thing to do when things can move around a lot. So anybody that's an engineer will appreciate that. Anybody that's ever dealt with the suspension system on a car or something like that will appreciate that. So driving down the street without dampeners, what will your car do? jump off the road. It's pogo stick. Ba-bang, ba-bang, ba-bang. So there's oil in there, slowing everything down so that it settles real nicely. Did you guys know that? By your suspension. So you've got your springs and you've got your dampers. Okay, so I like that. So I like the functional representation and I like to dampen it. AKA I'm a Bayesian. It's one way to think about it. The engineer's approach, maybe you would think of it that way. Okay, so you can't write down either of this stuff, but you can sample from F. So I can run this thing, but I don't get to see it. Okay? So there's a lot of models like that. So a lot of people that are doing some large scale computing, a lot of times they have systems like this. So common example of this is a climatology system. So I can change my inputs and I can generate real quickly some random realization of what I think the climate is going to look like. And so a lot of those systems are deterministic. The PDE solves. So they solve this big PDE system. So for every input that I plug into this, I have to solve a big PDE system, and then I need to jitter it somehow. Make it feel like randomness. The PDE solve will take 5 hours, something like that. Sometimes this is even very slow. So there's other things people will do. But the idea is that I can sample from this. So I can get X I's, if you will. So we can see these. Other data. And I'll just make a point, but we observe I'll write it like this, X observed. So that's what we actually get to see. Now I haven't told you the nature of X. You can think of it as a high dimensional thing right now. Maybe a big long vector. Without any loss of generality, think that it's a vector of realizations. Could be anything though. So here's ABC. Okay, let me call this the non-approximate Bayesian computation. This is non-A, B, and C. Let me write this down. So non-A, B, C. So this is non-approximate. This might be the easier thing to explain to you, and then I can tell you where the approximation comes in. Bayes computation. Okay, so this is a new algorithm. This is brand new. It's called non-A, B, and C. So you guys can code this up, write it up, submit it to journals. It's better than A, B, C in one particular way. It's not approximate, but there is a price you'll pay for it. So here's what we're going to do. So step one is I'm going to generate theta star from my prior. This is kind of my proposal, if you will. So remember what we were doing before, but I'm going to generate not from a proposal, I'm going to generate from my prior. So you might think of this as my proposal. I'm only going to get thetas out of this thing. But I'm only going to accept them under a condition. So step two, we're going to decide whether or not we want to accept this. So this is my prior, but also my proposal. Step two is I'm going to generate x's. X star is going to come from fx given theta star, what I just generated. I'm going to plug that thing in. So now I have an x star. I'm going to give you an accept reject criterion. This looks like a lot of algorithms. I could explain this through a lot of different algorithms, but I think explaining it through common sense is maybe even better. If x star is equal to x observed, then accept, I'm going to say theta t in all of this is going to be theta star. Else, repeat. This is a little different too than Metropolis Hastings. This isn't Metropolis Hastings. So this repeat thing right here is I might have 4, t goes from 1 to some large number in all of this, n. But I'm going to keep doing this over and over again until I satisfy this criteria. That's when I'll eventually give you a sample from theta. And I'm even going to say this. This is better than Metropolis Hastings, that I don't eventually converge. I converge every single time I get a sample. That's a perfect draw from the posterior distribution. So let me write that down. Fact. Every theta t is a perfect sample from pi theta given my data, x observed. This is our posterior, and that's actually our goal. We want a sample from it. Is that obvious that that's true? It should be. Tell me why that's true. Prove it to me. That sounds better, right?
You only accept your observed value?
Yeah, that's right. That's right. That's what the algorithm says. So I only accept when that thing hits my observed data.
Question. Does that happen with probability 0?
Doesn't matter. Don't worry about that. That's an efficiency question. These are questions of practicality. So if it's a continuum, then yeah. Since we're on a computer, no, but pretty close. You know, so might be excruciatingly small, the probability of acceptance. If x obs was a big long vector of almost continuous numbers, then it would be pretty practically 0. Not quite that bad. But let's just look at the algorithm. Instead of analyzing the performance of it, I give you non-approximate. Give you something perfect, and you gripe. So why does this work? What am I really getting in these 2 steps? These 2 steps give me something. You've said this before. What is it? What did step 1 and step 2 give you?
You get a measure of the quality of the prior, right?
Maybe. So I don't get the posterior, just step 1 and step 2. There's no observed data that's coming into step 1 and step 2. Haven't even considered it, so it's not a posterior. It's not a measure per se. I could probably turn it into a measure by using some of those functional forms. Keep in mind I can't write down f, so you're going to have a hard time with that.
So it enables you to write the likelihood, right?
There's no likelihood here, because I don't have observed data plugged in, and I'm not treating it as a function of theta. It's not that. Something you would get in your Stat 101 probability class. So a long time ago, you knew this concept. Now you've learned too many concepts, and you're mixing them all. What is that sample, x star, theta star? What? It's an estimate of what? I haven't tried to estimate anything with it. There's no observed data, so I'm not even estimating anything in those 2 steps again. There's no prediction going on. I haven't even used the observed data. There's no statistics even happening right there. In that other step where I include the observed data, I'm doing something with it, so maybe I'm estimating, maybe I'm doing something with it. But I haven't even touched the observed data in step 1 or 2. I just get x star, y theta star. It's a joint sample from joint distribution. So it's a joint sample. From whatever this thing is, I can write it down just like this. Fx given theta, pi theta. I can write that down as, I don't know, whatever you want to call this thing. I'm going to make up some notation. F pi is my new function. X theta. It's a joint sample from this model. That's it, right? That's not confusing. Help me out. Somebody tell me, I've never understood this before. If you didn't understand that, you didn't understand everything in your probability class, and all this stuff that we do is magic. Right, Dylan? Yeah, this is a joint sample, right?
Yeah,
Sure. Oh, come on. So it just is. So if I sample from something like this, fx theta, I can get a joint sample from this. What does it mean? I've got some surface over in here. These things live accumulated according to this distribution. Out here, I can partition this into fx given theta and some other model pi theta. What is this thing right here? This is just a margin, dx. So I just integrate that thing out. What is this thing right here? Well, this is proportional to that. It's a slice through this joint distribution where it's going to be centered at some theta. And it's normalized. So this gives me a joint sample. Joint samples that are conditioned on the observed data look like conditional samples. So this is a joint sample, and I only want the ones with the right conditional property, i.e. the ones that are conditioned on this. So what I'm getting when I end up accepting right here is I really have a joint sample of theta and x where x is always the observed x. So I really have a conditional sample right here. So step 1 and 2 give me a joint sample, and then I take the ones that are fixed on some line or plane, whatever the dimensionality of all this is. Then I have a conditional sample. Which sample do I have? I have the conditional sample from this model. Does that make sense? Non-approximate. That is. Let's talk about the one downside to this that's obvious and immediate. This had better be proper to even do this. So if I'm going to sample from something, it better be something I can sample from. Try to sample from an infinite uniform. Going out, you cannot do it. It's not possible. What does it even mean? The actual probability mass is 0 everywhere. So it doesn't even make sense. So you cannot sample from an improper prior. So it must be proper. Prior must be proper. So if we're estimating something and we've forgotten everything we learned about hypothesis testing, sometimes we like some of these improper priors. They have good properties.
I don't get the for loop there because like theta t is not related to theta t minus 1, right?
Well, through x odds it is. So I'm generating just any old thetas, but I'm accepting under some condition that relates all those thetas. So I'm getting joint samples, and I'm only going to take the joint samples. So if you think of it like this, maybe this is theta, and this is x in 2 dimension. If I'm getting all these samples, that's step 1 and 2. The ones that I'm taking, I could run them all and collect them all, and then maybe there's an x obs right here. If this was just a 1-dimensional data set. And so I'm only going to take the ones in here, along there. Those samples are distributed according to my posterior distribution. So I can project those ones down right here, and that's going to be my posterior, coming under those. If I just look at how those ones are distributed. If I projected all these other samples down here, they would be distributed differently in the margin. And so it's just that conditional slice. So they are related to each other under x ops. the ones that we accept.
So to improve the performance here, could you instead sample from the joint sample given your observed value?
Yeah, maybe, but then you already know how to do what we don't know how to do. How do you do it? We can't write down F is the problem. So you might say Metropolis Hastings, but again, you can't write down the likelihood. So you're gonna have a hard time doing that because you can't express that functional relationship. So again, let me remind you, you can't write this down, but you've got some sort of a black box right here that you're able to sample from it, but you can't write it all down. Example of that, big climate models. So how many Fortran lines of code are in these like semi-realistic climate models? Millions. And they're doing some big PDE solver and it's got some jitter on it as well. So they're like these pseudo-stochastic models, but they have the look and feel.
Could you then weight all your theta samples by the 2 norm distance from x to the observed value?
Maybe, right, okay, so now we're gonna get into a new algorithm. So this is exact, it has a lot of pitfalls. Maybe we can come up with reasonably calibrated priors. You can probably do it. If you like the flat prior for, let's imagine theta was a mean and a normal distribution and you're like, ooh, it's shift parameter, I like flat. Well, you could choose a very, very diffused normal and your inferences would be about the same. If you knew where to center that normal, you'd probably speed up this algorithm and get more acceptances faster and not weight things way out in an area where they have no weight under the posterior, i.e. condition on the data. How do you know how to do that? You really don't. But you could use a very diffuse prior right here. Kill the efficiency of your algorithm, but maybe we don't care about such things. Most people do. Here's the the approximate version. So here's ABC, and Ben's got it. ABC is same thing. 1 theta star comes from my prior. Proper, I can do that sampling. X star comes from my sampling model. Then we do something like this. If, now I said X was presumably high dimensional even though I represented it one dimensionally here. What you might do is you might take some norm on X star and compare it to X observed. You'd use some norm, and maybe I end up using some norm over here. So I'll just say some other norm. Okay. So I'll call this norm 1. This is probably the same norm right here. You wouldn't change your norm because it's the same data. And this is some other norm. Maybe let this be like absolute value or something like that. Maybe they're squared error, maybe they're absolute value, but they measure differences between the sets. So this is some. I'll say more about it in a second.
Is this the L2 loss?
I haven't said yet. That's why I said it's some norm. Okay, I'll discuss it. This is the approximation step, and all approximations have repercussions. I didn't make this up. So some norm. Okay, and what I'm going to do, if this thing is less than epsilon, some distance, then we accept. Theta, I'll just write it this way, accept theta star, else repeat. Okay, so that's the idea. Then,
So if you take the difference of norms, then if they're equal but opposite, you still accept.
if they're equal but opposite.
So like the X star you sampled is -3, but the one you observed is +3.
Could be, yeah. So in a normal case, the antithetic sampling actually does work though, if it's centered right. So there's all kinds of repercussions here. This is what Ben is going to get at and Christina are going to bark at. Which norms and which distance? That was that whole meltdown where Fabrizio says, that's not mine. I don't know. I didn't pick that. Some other guy did all that part. I'm talking about setting up the model. I helped write the paper. I didn't do that. That was the discussion in everything. So it turns out, which norm do you use here on the data? Turns out if it's a sufficient statistic that you're using, then you're using something that has information about theta. So let me just write this down. If X right here is a sufficient statistic. So you'll notice that I didn't say this has to be one-dimensional right here. This could have knocked out a two-dimensional thing. Imagine theta was our variance and our mean parameter, so we have a two-dimensional thing. Well, then I might kick out S squared and X bar and check how close they are to my observed. And I might check them both separately. That's what this is trying to generalize, this statement. So there might be two distances that you monitor. But basically, if this thing is sufficient, and epsilon is small, this is good. Probably. I.e., the approximation is probably pretty close. If you don't have sufficient statistics and you don't know what they are from your model, because you can't even look at F, this isn't going to help you a ton. And so there are a lot of papers that show this thing can work well, and there's a lot of papers that show that it can melt down a lot, and it can have a lot of problems. So what do I usually say if you don't know? Simulate it. Check. In cases where you know, and if it's in a problem like you are used to dealing with. How will you know that something is a sufficient statistic without being able to write down F? I don't know how to do that. So you have to give me F for me to tell you something is sufficient. So I don't know the answer to all these questions you're about to ask. But that's ABC. So I joint sample and I take ones that are about close to the data set that I've observed. If I take X to be the whole data set, that's always sufficient. But then the probability of me hitting the exact data set goes down to vanishingly small. So you usually want to reduce it to some statistic that's small dimensional. And you hope to do it for a sufficient statistic. Have those things that you're measuring and seeing how close they are from the output from your simulation model to the sufficient step. So a lot of pie in the sky. I've never used this algorithm, so too worried about it. So, but you do see people that they're like, well, I have simulators, I want to do Bayesian stats. This is what I can do. And if they haven't gone through all the work to verify that maybe what their statistics are that they're using are good, how do they pick their distance? There's a little bit of help right here. What people will do is they'll sometimes start with kind of a bigger epsilon, then they'll use a smaller one and a smaller one and a smaller one and a smaller one, and they'll look at some statistic from their posterior distribution, and then they'll extrapolate that all the way to what would have happened when epsilon was 0. So they'll do an extrapolation. More statistical things to worry about. And so can work, might not, and Fabrizio didn't convince any of us that he's gone through all those checks, so his answers may have been good and they might not have. It might not have anything to do with this model decisions, how he set up these queues, whatever that problem was. That's ABC. Okay, next time I want to come back after the break and talk to you about model selection on regression models. And I'm going to show you several ways of doing it. I'm going to show you shrinkage methods, like lasso. It's very popular. And I'm going to show you how to do the point mass prior thing and apply that in a Gibbs fashion. So you already know enough to metropolize that. You know what the prior is, you know what the likelihood is. All you need is a proposal. But I'm going to show you how to write down all the full conditionals so that you don't have to come up with a proposal. And they're things you already know, and we've already computed. So again, all this stuff is easy. After that, I'm going to show you Dirichlet processes, and then I'm going to teach you a little bit about decision theory. So I'm having a hard decision on where do I teach decision theory, in this class or my inference class.
Is there an algorithm for that?
No, unfortunately. And I'm not even sure I'm close to conversion. But I'm going to teach you a little bit about it and try to figure out how to restructure this stuff. So I've taught you a lot of algorithmics. Maybe I want to go back to teaching some theory right at the very end. So I'll show you some cool things and some other paradoxes, stuff people argue about. Super fun, never ends. That's it, you guys. Have a great Thanksgiving. Be thankful for something. Go enjoy nature. The weather's supposed to be pretty good, so days like today are good days in the fall. It's warm outside. So time to recalibrate. Oh, homework, yes.